Many mathematical subjects all have in common that they're kind of about two things. They're about objects. So what is the stuff that we study in that discipline? And they're about functions. Sort of what are the ways in which we can turn one of those objects into another? When we think about linear algebra, the objects, the stuff that makes up linear algebra that we study, are vectors. And we've just finished describing how vectors are defined by their mathematical properties, their qualities that they enjoy. And the qualities that vectors must enjoy, by definition, are that they must be able to add with other vectors, and they must be able to multiply by scalars. But that's it. Any system in which I can do those two things in a reasonable way is called a vector space, and therefore it gives us a platform in which to study linear algebra. So if the objects of linear algebra are vectors, then what are the functions? What kinds of functions can we study in linear algebra that can transform one vector into another vector? So in this set of videos, we're going to take a closer look at what is it that makes a function a so-called linear transformation. That's the name that we give to the kinds of functions we study in linear algebra. And, really excitingly, we're going to ask the question, how is it that we can take a linear transformation, the kind of function we study, and define it by it a matrix that completely represents the action of that linear transformation and gives us a way, computationally, to study the properties of that transformation. So the kinds of functions we study in linear algebra are called linear transformations, and how they work is that they are completely powered by the properties that vector spaces enjoy. So we know now that vectors are vectors only because they know how to add to other vectors and they know how to multiply by scalars. And that's all. That's all the structure that we get to take for granted in linear algebra. And since it's not a lot of structure, linear algebra is super flexible, and we can use it in a lot of situations as long as we have objects that know how to do these two things, add to other vectors and multiply by scalars. So the kinds of functions that therefore come to the table are going to be functions called linear transformations that respect the structure that vector spaces have. So a mathematician, if we're putting a sort of a fancy speak hat on, will say a linear transformation is a function which respects the structure of a vector space, which respects addition, and which respects scalar multiplication. And that's just another way to say that whichever order we operate, the result is the same. In other words, if we take a linear combination of some vectors and then we apply a linear transformation, then the result is exactly the same as if we had first applied the linear transformation to each of those vectors and then done the linear combination. So linear combination first, transformation second, gives us the same result as transformation first, linear combination second. It's a bit like the commutative property of multiplication when we're thinking about basic arithmetic on the real numbers, for example, right? If I take multiplication and I do it in one order versus the other, it's a different problem, but those two problems have the same result, the same product, the same solution at the end of the day. So linear transformations are transformations that respect linear combination. Linear combination first, transformation second is the same as the transformation first, linear combination second. So what does that look like in practice if we put some notation to this idea? Well, suppose that I have a couple of vectors v and w. I can first form some linear combination of them. So c1 times v plus c2 times w. If I do that first, and then I apply some linear transformation, so I wrap those into the input of some function we call t. Then if t is a linear transformation, that should be the same thing as if I had first applied the transformation to the vectors. So if I had first done t of v and t of w separately, and then after that applied the same linear combination, so c1 times the first one, c2 times the second one. So that's what I mean by doing combination, then transformation, versus transformation, and then combination. And if t is a linear transformation, that means that these two things have to agree. So mathematically, just to make this precise, if we have two vector spaces x and y, and a function for which x is the domain and y is the codomain, we're going to call that function a linear transformation only when for all vectors v and w that I choose from the domain, and all scalars c1 and c2 that I choose from among the real numbers, that this identity will hold. That the result of doing a linear combination of these two vectors first, using c1 and c2 as the weights, and then applying my function, is the same result as applying my function to these vectors first, and then forming the same linear combination of the results. So what does this look like geometrically? Let's think again, let's keep our feet on the ground here and think about R2 for a second. What linear transformations do to R2 is that they can turn a uniform square grid into a uniform parallelogram grid. So I like to think of it as if I start with some ordinary graph paper, and I've sort of tried to color my vertical lines here red and the horizontal lines here blue, but if I start with ordinary graph paper and I apply a linear transformation to that graph paper, what I'm going to get is a different kind of graph paper, if you like. It's still going to be a grid, but now it's going to be kind of a grid potentially at an angle. Right? And so it's going to transform a point in the xy plane x into an image over here, t of x, but it's going to transform the whole xy plane along with it. And in doing so, this uniform square grid turned into a uniform parallelogram grid. And here's a key observation. This is in fact going to be the key observation that's going to get us to matrix land in the next video. That because this uniform grid is transformed into a uniform grid, and because we have linearity, we have linear combination that defines my vector space, this transformation T, this grid on the right, if you like, is going to be completely determined by what happens to just one of the squares in my grid on the left. So this little yellow highlighted, what I call the unit cell here, this is just the square in the xy plane at 0, 0, 1, 0, 1, 1, and 1, 0. So this little square, that the entirety of this linear transformation will be completely determined by what happens to this little square. And in this example, this little square here becomes this stretchy parallelogram right there. But that's all we need to know, because of linearity, to define what this transformation does to the entire xy plane. So T's action on the entire space is determined completely by its action on this little tiny unit cell. Another way to say that is to think of this unit cell, this little tiny square, as having its sides defined by the vector e1 and the vector e2. The vector 1, 0, which is the horizontal side right there, and the vector 0, 1, the vertical side. Because of linearity, if you tell me what my transformation does to e1, so if you tell me where the purple vector lands in its image in the codomain, so that would be this purple vector right there, and if you tell me what this transformation does to e2, it lands on this green vector over here on the right, if you tell me what this transformation does to just those two vectors, then because of linearity, because of this property, because of its ability to respect linear combination, you've now told me, first of all, everything we need to know about what happens to this whole unit square here. It becomes this parallelogram. But also, you've told me what happens to everything inside of the xy plane. So what that's telling me, so for example here, t of e1, this purple vector, looks like negative 1, 1, and t of e2 looks like negative 1, 2. But if you tell me what this transformation has done to just those two vectors, you've told me everything we need to know. Why? Well, suppose that I have some other vector x in my xy plane. Then because e1 and e2 form a basis for the xy plane, that means that I can express this other vector x uniquely, in only one way, as a linear combination of e1 and e2. So I've chosen this to have the coordinates 4, negative 1 in the xy plane. And so that means, in particular for this basis, that x is equal to 4 times e1 plus negative 1 times e2. Now, if I apply the linear transformation t to that thing, then on the one hand, I could do the linear combination first, 4e1 plus negative 1e2, and then apply t, which is what this is showing us in the picture. But because t is a linear transformation and it respects linear combination, that means that instead of applying t to x, what I can do is instead apply t to e1 and apply t to e2. In other words, find the purple vector, find the green vector, and then wait until the end to apply the linear combination. In other words, the image of 4e1 plus negative 1e2 is going to be 4 times the image of e1 plus negative 1 times the image of e2. So in other words, if x is made from 4 purples and negative 1 green, then the image of x will be made from 4 of these purples added to negative 1 of those greens. That's the magic of linear transformation. So what we have just sort of won for ourselves is that if it's true that a basis for a vector space determines all vectors in that vector space in a unique way, then it's also true that the effect that a linear transformation has on that basis will determine the entirety of that linear transformation. And as we'll see next, we'll determine a matrix for that linear transformation.